Arrays are great, but they have limitations. Let's understand why. Let's look at array limitations. Here we have an array with elements A, B, C, and D. First problem, what if you want to insert at the beginning? You must shift all elements to make room. This takes O of n time, that's slow. Second problem, delete from the middle? Same issue, you have to shift everything after it. Again, O of n time. Third problem, arrays have a fixed size. This means either you waste memory, or you need expensive reallocation. So what's the solution? Linked lists. A linked list is a dynamic data structure. Each element points to the next one. The best part? Insert and delete operations take constant time O of 1. Here's how it works. Each node has two parts. First, the data, that's the actual value you want to store. Second, a pointer, this is a reference that tells you where the next node is. The last node has a special pointer value of null, which marks the end of the list. Let's see insertion in action. We'll insert a new node at the head of the list, and it takes constant time. Step 1, create a new node with the value 9. Step 2, make this new node point to what's currently the head of our list. Step 3, update our head pointer to point to the new node. Done. Only 3 simple operations equals O of 1 time. No matter how long your list is, insertion at the head always takes the same amount of time. Now let's talk about memory layout. This is important. Arrays use contiguous memory. All elements are stored together in a continuous block. Like having books lined up on a shelf, they're all next to each other. Linked lists use scattered memory. The first node can be anywhere in memory. It just needs to know where the second node is. The second node points to the third. And so on. They can be anywhere in RAM. This is powerful because you don't need to find a large contiguous block of memory. And it's easy to grow your list dynamically. Let's look at the code. Here's how we define a node. The node class has two parts. The init method takes the data you want to store. It sets self.data to that value. And it initializes self.next to none, meaning it doesn't point anywhere yet. For example, if you create a node with value 42, accessing node.data gives you 42. And node.next is none initially. Now let's see how to insert at the head of the list. First, create a new node with your value. Second, point this new node to the current head. Third, update the head to be your new node. That's it. Constant time O of 1. Here's a practical example. Start with a list that has just one node containing 5. Now insert 3 at the head. Then insert 7 at the head. The final list now reads 7 points to 3, which points to 5, which points to null. There are 3 types of linked lists, each useful for different scenarios. Type 1, singly linked list. This is the simplest. You can only move in one direction, from the start to the end. Node A points to node B, which points to node C, which points to null. Type 2, doubly linked list. Now you can move both forward and backward. Each node has 2 pointers, one to the next node, and one to the previous node. So null connects to A, which connects to B both ways, which connects to C both ways, ending at null. Type 3, circular linked list. Here, the last node doesn't point to null. Instead, it points back to the first node, creating a loop. Node A points to B, B points to C, and C points back to A. Now for time complexity analysis. This tells you how fast operations are. Insert at head, constant time O of 1. Lightning fast. Insert at tail, usually O of n because you need to traverse the whole list. But it's O of 1 if you maintain a tail pointer. Delete at head, O of 1. Also constant time. Search, O of n. You might need to check every node. Access by index, O of n. You have to traverse from the beginning. So when should you use linked lists? Use linked lists when you have frequent insertions or deletions at the beginning, when the size is unknown or changes a lot, when you don't need random access to elements, or when you're implementing stacks or queues. Avoid linked lists when you need fast random access to any element, when you're searching frequently. If memory overhead is a concern, remember, each node stores an extra pointer. Or when cache performance matters, arrays are better for cache locality. Let's see some real-world examples where linked lists shine. Example 1, Browser History. When you click the back and forward buttons in your web browser, that's using a doubly linked list to track where you've been. Example 2, Music Playlists. The next and previous song buttons in your music player use linked lists to navigate between tracks. Example 3, Image Viewer. When you're viewing photos and clicking next or previous, that's often implemented with a linked list. Example 4, Undo and Redo Functionality. Applications maintain your operation history using linked lists, so you can undo and redo actions. Follow at srj.learn. Master data structures and algorithms with me. I post new videos every single day.